Yeah, so today we're finally going to get to cycle problems. We've talked about the three laws of thermodynamics. We've talked about isothermal expansion. We haven't gotten to adiabatic expansions and compressions. That's the next lecture. But today we're going to talk about, we're going to use an isothermal expansion, and we're going to do our first cycle problem. So it's kind of a big deal. Okay, so I picked a 3-leg cycle just because it's simpler than a 4-leg cycle. Now, the exam is not for another week or so, a little more than a week. And last time on the exam, we studied the 4-leg cycle, the Carnot cycle and the Otto and the diesel cycles. And everybody got used to 4-leg cycles. And so then on the exam, I gave a 3-leg cycle because it's a shorter problem, and everybody locked up. They're like, I don't know what this is. And so they just couldn't do the problem. So it was really bad. So we had to come up with a plan to fix that. But we start with the simple one, a simple 3-leg cycle. Now, what do we mean by a cycle? Well, look at this PV. Always start with the axes. So we start with the axes. We have pressure versus volume. Now, temperature is in here too, and it may come out like, say, temperature axis here. So, but we're just kind of looking at the PV projection on the PV plane, and we've got 3 points here, but notice it comes back to the original point. So that makes it a cycle. As long as it's closed, it's a cycle. It can have as many legs as you want, but if it's closed, then it's a cycle problem. And so going through this cycle, the working gas, and in this case I think it's gonna be helium or neon. The working gas is doing work. This is the volume. It's expanding and then it's contracting. And so what we want it to expand and push on, say, a piston, and then we want to compress it back to its original state and start over. So this cycle should produce some work for us. Notice the arrows, they're going in a clockwise manner. So you start with this expansion, and it's at a high pressure, so there must be a high temperature up there. So we're doing an expansion with high temperature and pressure, then we're dropping the pressure at a given volume, so it must be cooling down here. Because how can you cool down a gas? I mean, how can you cause the pressure to drop in a container? Well, you can cool the gas down. So we cool it down way far here, now we have a low pressure, and then it's real easy to compress at an isotherm, to compress a gas that's cold. And so we cool it, we compress it, and then when we compress it, the pressure goes back up to 10, and we've reset the system. So before beginning any of these calculations, ask yourself, are there any isothermal processes? Because they depend upon delta T, delta U and delta H are 0 in an isothermal process. So that is a helpful thing. To remind you of the equations, delta U is the CV times delta T, the heat capacity constant volume, and delta H is the CP times delta T. So if delta T is 0, then delta H and delta U are 0. Another thing that you can look for is, are there any adiabatic processes? We're going to study that next lecture. So we really don't know anything about those, but if there is an adiabatic process, then Q is equal to 0 and delta U is equal to the work. So we can figure out in those cases what delta U is from the change in temperature. It's just temperature times CV, and then that is the amount of work that was done or was put into the system. And then there's the constant volume processes. If there's a constant volume process, then you can't be doing any expansion work, because expansion and compression change the volume. And if you're stuck at a constant volume, then the work is 0, and then delta U is the change in heat. We have one of those in our cycle. We have that vertical line on the volume axis. So there's no work done in that particular spot. And so this is what we've got. We can evaluate this. At the top, we've got expansion against a constant pressure. Well, we know an equation for that. We know that one of the work equations is minus P external times delta V. And delta V is easy. We've got the maximum volume and the minimum volume. We'll put numbers on those in a minute. Then we have this constant volume cooling. Remind me again how I know it's cooling. Look at see the arrow, the direction of the arrow? We're dropping pressure at a constant volume. So how are you going to get pressure to drop? But you cool the gas down and that'll drop. the pressure. So this is constant volume cooling. If the arrow was pointing up, this little arrow here, if that was going up, then it would be heating, constant volume heating, but we see that direction of the arrow, so it's cooling. And then we have this isotherm. Delta T is 0, so H are equal and also 0, and Q equals minus W. Because Q plus W equals delta U, and so if delta U is 0, then Q and W have the equal magnitude but opposite sign. So this is the underlying information about the different cycles, okay, about the different legs of a cycle. So each one of these is called a leg. So you have 1 to 2, 2 to 3, and 3 back to 1. So there's different legs of a cycle. Okay, so the very first thing, well, I say the first thing is to figure out if you have isotherms and things like that. The second thing is to do the state variables table. So you've got these points right here, and every one of these points is going to have a state variable, set of state variables associated with it. So at point number 1 right here, we've got 10 atmospheres. This is just given right here in the problem, but I'll go ahead and put it on here. 10, and then we'll have to calculate what it is. 1 liter of gas, and then 10 moles of gas. And so with that, we could figure out with the ideal gas law what the temperature is. And then over here at 2, so even though temperature is not in this whole diagram, temperature is really important. And so we'll have to figure out, using the ideal gas law, what these various temperatures are. And then state 2, because it has the same pressure, it's also 10 atmospheres. And then we've expanded, though, at point 2 to 20 liters. 10 here. So this is 20 liters. And this is 1 liter way down here. And so it's up to you which one you choose to do first, right? We've got 2 here. Point number 1 and point number 2 have got just one variable unknown, right? The temperature. So we can solve for the temperature in either one of those cases. So let's do this number 1. So that's P1V1 over NR. We got 10 moles of gas for N. And in this case, the R we want to use is what? So if you see if you know it from memory.
What's your
Yeah, so this is the R with 0.08206 if you want a few more sig figs. Liters, atmospheres per mole Kelvin. Because it has all the units that we want. It's got atmospheres and liters and moles. To put that R in there and solve for your temperature, and it's really quite a cold temperature, 12.2 Kelvin. Now, what else? By solving for the temperature at point number 1, we can fill out another square on our table. This is way better than Sudoku. Sudoku is ridiculous, yeah. But it's the same mental idea. It's like, okay, 1 and 1 is connected to point 2 and 1 is also connected to point 3. But which one of those is going to have the same temperature? 3, because it's an isotherm. So everything along that isotherm is 12 Kelvin. So we can come right over here and we can say that isotherm is 12 Kelvin. Okay. Now, what's that? What?
like we know it's an isotherm because that's given? Or
It's given, yeah, it's given, yeah. And then later when we have the Carnot cycle, we'll have 2 isotherms and 2 adiabats. And you've got to memorize kind of how the cycle is constructed to know which ones are the isotherms and which ones are the adiabats. And that's something that people mess up. So it's something to pay careful attention to. But if a problem like this, there's no, like on this cycle, it's not a classic one like the Carnot cycle. So you've got to have that question. If it's an isotherm, then this. If it's an adiabat, then this. And so you would have to figure out which it is. Yeah. Okay, so then the point number 2, we could calculate P2 V2 over NR, and we get a pretty high temperature relative to 12 Kelvin. That's 243.7. So something's been going on. If we went from 12 Kelvin to 243 Kelvin, we were putting in a lot of heat. Handwriting on this new tablet is really weird. Okay, it's just enough different that my letters are looking weird to me. Okay, maybe y'all can't tell any difference because it's all bad. Okay, so you see, you can't get it to go from 12 Kelvin to 243 Kelvin without putting in a ton of heat. So we've been putting in enough heat to keep the pressure constant. So we're expanding against a constant pressure, but we're dumping in a whole lot of heat. Okay. So that's what's going on in terms of this cycle. And then over here, to cool down from 243 down to 12 Kelvin, let's say up here, heat in, and this is going to be heat out. And then this also, this isotherm, because we're compressing it, which would typically heat up the gas. So, where's my pen? Yeah, so this also has heat out. Normally when you're compressing a gas, it warms up. Okay, the gases are getting, in a smaller space and, upping their energy. And so if you want to keep it the same temperature, you have to get that heat out of there. And so how is it easy? It's pretty easy to have an isothermal compression because you just have the gas in a container that conducts heat. So you compress that gas and the heat goes out through the walls, and maybe you have water to carry it away, kind of like in your engine.
So why is it heat out in the isotherm?
Because we're compressing the gas. So by compressing the gas, we're doing work on the gas, but we want it to stay the same temperature. And so if we want it to stay the same temperature, the work we do on the gas would generate heat, but the heat has to be pulled out to keep it at the same temperature. Yeah. Yeah. And so then lastly, the point number 3, we just have to solve for the pressure at point number 3. And so again, it's going to be the ideal gas law rearranged for nRT 3 over V3, and so we have half an atmosphere. So we cooled it down to 12 Kelvin, and so the pressure really, really dropped to 0.5 atmospheres. Probably not a realistic cycle, but it still doesn't matter. It's just a good practice for the numbers. Okay. So this is what's called the state variables table. This has got to be done for all of your problems, and this is one of the things I'd like to see on the handwritten work is show me the state variables table and calculate all of your points. Because now we can calculate delta V and use that to do work. Now we can calculate delta T and use that to get energy and heat and work and so on. So the deltas are going to be like for leg 2 to 3, it's going to be final is the 3 values and the initial are the 2 values. And so we can do our deltas that way. So this is sort of a starting point to get your state variables all laid out. All your major points along a cycle, get those identified so that you can calculate deltas. So now let's calculate it. So these are some of the equations that we have from earlier lectures. Like we have that work equation, which is expansion against a constant pressure. So minus px delta V. And so that's minus 10 atmospheres, goes across from 1 to 2. Oh, and this is, all of these equations, we're just doing segment 1 to 2 or leg 1 to 2. So you can see that up here. So we're just doing the first one right here. Segment, or I call it leg. Leg, that's maybe how I was taught. on that leg of the journey. And so we can calculate that work, and it's 10 atmospheres. And here's the thing, it expands to 20. A lot of people will just make a mistake of thinking that 1 is the same as 0. It's like I started at 1, I went to 20, so the difference was 20. No, it's not. It's 19. You know, and you're looking like, why would people do that? And that's what I say too. Why would people do that? But they'll just write down delta V equals 20 because they discount the 1, but it's not. It's 19. Okay, so I've seen it all, I guess. So don't forget the -1 here. And then, but that gives you your work, but it's not in the happy units of joules, right? It's in liters atmospheres. So this is where we have to figure out how to convert from liters atmospheres to joules. Now, where did this number come from? It seems kind of random. But you can remember this one because this is your two gas constants. So you have 8.314 joules per mole Kelvin divided by 0.08206 liters atmospheres per mole Kelvin. This is a shortcut if you can't remember it, 101.325. The per mole Kelvins cancel, and you have the joules per liter atmospheres, and you take 8 divided by 0.08, and it's about 100, 101.325 to be exact. And so that's our conversion from liters atmospheres to joules. So you get negative 19.3 kilojoules. Don't drop your negatives, that's the problem. So that tells us that work came out of the system. It did work on the surroundings, 19.3 kilojoules of work. Let's calculate delta H and delta U and Q. So we have delta H is using the heat capacity at constant pressure. This was for 10 atmospheres, or 10 moles of a monatomic gas, like helium. And so helium, you've got 3/2 R for translational, and then plus an R to make it CP, right? So this was CV, and then we add an R to make it CP. So that's where we get the 5/2 R, right here, because it's CP. And then we have delta T, so 244 was the temperature at 0.2, and 12 Kelvin was the temperature at 0.1. And so then we get 48.2 kilojoules, and look, it's a positive value. And that tells us that work was done that tells us that heat was put into the system. So 48 kilojoules of heat went into the system to push on the piston and raise the temperature. There was one of the equations on the sheet at the end of one of the lectures at the beginning was kind of a summary of equations, and it was CV plus R is equal to CP. It's just one of the definitional equations. So if you know all their CVs, which we do, right, the translation, rotation, vibration for CP, or CVs, then you just add an R to get the CP. So then for delta U, we would have essentially the same calculation, but instead of 5/2, it'd be 3/2 R. And so it's going to be less than the 48. It's going to be 28.9 kilojoules was the change in internal energy. And now that we know delta U, we can kind of use that first law of thermodynamics that any change in internal energy is going to be found in heat and work. And so delta U goes here, and the work from up here comes down, and then we can find the heat. So 28.9 kilojoules internal energy change minus the work that was done, and the work was negative, so again, it's another opportunity for you to mess up by dropping the negative, and we end up with the 48.2 kilojoules. So we see the delta H and Q are the same. We call that the heat of reaction. So we put that much heat into the reaction. There's a lot of different ways you could calculate these. We could have said that delta H is equal to Q and be done with it. But I just wanted to show you the calculation of delta U. Well, it's helium. So we're dealing with the working gas of helium right here. So trans only. We don't have any rotation for a monatomic. Yeah, that's okay. Yeah, that's all right. I want to see that light bulb. Yeah. But we couldn't, so that's a great, let me reemphasize that since you asked a good question. Um, we have this block right here where we have to calculate our heat capacities. And I'll just emphasize must know the type of gas. And so we have three types: monatomic, linear, and nonlinear. And those will have dramatically different heat capacities because of the 3/2 R for everything has 3/2 R for translation. But when you get to linear, you have another 2/2 R for the rotation. If it's nonlinear, you have 3/2 R for rotation. So, so those are the major ones. We're not going to deal with any vibrations in these gases. So it's really just the difference in rotation. Either it's non-existent for a monatomic gas, or it's 2/2 R for the linear, or 3/2 R for the rotation of a nonlinear, and then all of those are added to the 3/2 R for translations. Yes. Go ahead.
So for delta H, it's calculating translation and rotation, but delta U is only translation.
No, it's confusing. Okay, for the delta H, it's CP.
Okay.
So let's just do a practice here. So let's where's my pen? Okay, over here. All right, so let's do monatomic. Is CV is equal to 3/2 R. We got that right. And then that means CP is equal to CV plus R. So then it's 5/2 R for CP. Because I have 3/2 already. Adding another R is the same as saying adding 2/2, and so we'll just keep it all in units of halves. So I'm just adding 2 more halves of R to CV, and I get CP. So
Okay.
that's where the 5/2 comes from. Now let's do a linear. So everything has translation, and then I'm going to add in 2/2 R for rotation. So that equals 5/2. And then CP is going to equal 7/2. I added another 2/2 to give the CP. And then let's do nonlinear. Then I have another 3/2 for the rotation. Oops, I did 3/3. Why did I do that? See if I can erase. And so this is 6/2. We could just say 3, right? But we'll say 6/2 just to keep it consistent. And then CP, we add another 2, so it'd be 8/2. for nonlinear. So that's everything we could possibly come up with. So if I'm using like a nitrogen gas or whatever, that would be the linear one. If I'm using steam, then that would be the nonlinear one.
Okay, you know it's CP.
Yeah, so it has to be delta H is using CP and delta U is using CV.
Okay.
Yeah,
Okay.
yeah. So that's just all of the different ways these equations work together. Now it sounds impossible to remember, but it's not. It's you have this equation for delta H and delta U, it doesn't change. The only one that's kind of weird is work, because this is work expansion against the constant pressure. You could also have work associated with an isotherm, and that's a different equation, and we'll do that one later. And then we have the different adiabats, and there's no work equation for adiabat. We calculate the delta U and then use that to calculate the work. So anyway, it's not too bad. All right, now let's do segment 2-3. So this is the one where we cool things down at constant volume. So since it's a constant volume, this makes the work equation very easy. It's 0 because, do y'all know the upside down 3 dots? Yeah, that's because. So this is saying it's equal to 0 because delta V is equal to 0. So there's no work done on segment 2-3. And since there's no work done, then down here, the heat is equal to the delta U, because W is 0. So here's the calculation for the delta U. Here we're using CV, 3/2 R. And it's important to pay attention to the delta T here, because it's final minus initial. We're just, a lot of students and myself occasionally are biased against negative numbers. So we like to do big minus small because it's easier to do in our heads, but it's not big minus small, it's final minus initial. And final is smaller than the initial, so this temperature change is negative, which means the energy change is negative, which means the heat came out or energy came out of the system. Okay, and then we'll do the same thing for CP, but now it's 5/2 R for CP. 12K minus 244, and so we get the negative 48.2 kilojoules. So that's how much heat came out of the system.
With the, I thought delta H was CV.
Delta H is CP. Yeah. Now these are on different rows than they were on the previous page.
So it switches.
Well, I just did delta U first instead of delta H on this problem. So see on the previous page, delta H was the second line, and it's using CP. Yeah, and then the third line is delta U and using CV. But on this one, I just calculated it. I calculated delta U first and then delta H. I don't really know why, but that's just the way I did it. But it's correct that U goes with CV and H goes with CP. And then I just changed the sign on the delta U. No, I don't change the sign. It's the same. So Q is equal to that change in internal energy of minus 28, because work is 0. What made this leg easier to calculate than the last one is it's because delta V is 0. So when delta V is 0, there's no work done. So that makes it pretty easy. And then the last leg, 3 to 1, 3 back to 1, we're resetting the system. And so we have isothermal compression. So isothermal, so delta T is 0. So that means delta U and delta H are 0. If delta U is 0, then Q and W are equal in opposite signs, equal magnitude, opposite signs. So I can't find Q until I find work. And so we know the work for isothermal compression. So we put in, again, 10 moles. We have R there. For this R, we're going to use the 8.314. And then it's V final over V initial. So that's an important point. So hard to see this little pen. So this is final over initial. This is probably the most subtle place right here to drop you're not dropping a negative. You know, normally what a drop a negative is you have a negative sign in the equation and you do all the math, but you don't remember that negative sign there. And so that's what we call dropping a negative. But if you get these volumes upside down, think about the logarithm. It passes through zero at one. At one, it's zero. So if it's a fraction that's less than one, it's negative, and if it's a fraction that's greater than one, it's positive. So if you swap initial and final, it goes from greater than one to less than one, and it'll change that sign. You'll get the same magnitude, you'll get to the opposite sign. And so that's a problem. And that's a way to swap the sign on your work and not know it. Like you can look at this and you can see this negative sign and you can say, well, I still use that negative sign, but your natural log flipped the sign and you got heat flowing in or work flowing in when it should be flowing out. And when you can catch that, when you go all the way around, your energy should the delta U for the whole cycle should be zero, and delta H should be zero. And if you screw this up right here, it won't be zero. You're going to get something. So you can kind of do a checksum at the end of your problem. So here we are. This much work was done on the system. See the positive sign? So let me just emphasize that. So it's positive here. So the system is the helium gas. That's the working fluid, and it's pushing the piston. So that's what we mean by the system. When the working fluid pushes the piston, it's doing work on the surroundings. And all its work values are negative because it's pushing on the piston, doing work externally. Then when we reset the system, we compress that gas into a smaller space, work is positive, which means we're putting energy into that working gas so it can start over. So we're doing work on the system, putting energy into that working gas, and it's getting reset to start over again. Yes?
I'm just trying to look at like the keys.
Mm-hmm. 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 Because Q Q is not a state function. So it's not going to go around and cancel out. But the U and the H are, and they will cancel out. So let's look at that. That's the next calculation to see what the cycle numbers look like. So here we have, because of the state function U, it go around the cycle. Remember we said the energy of the system at point one is going to be the energy at point one no matter how it got there. And going around a cycle is a way to get there. Like you're at the second floor, you go up the stairs, you take the elevator down, you come up the stairs, you're back at the second floor, you have the same energy you had before. Yeah, the same energy. Now you've done work and you've had work done on you, but you have the same energy. Your energy is just a function of how high you are off the ground. Why is what not zero?
You said
I was saying if you're at state one, at state point one, you go around the whole cycle, you're back at state point one, and your energy should be the same. Now, you've given off energy and you've taken in energy and you're back to where you were. Just like if we're on the second floor, we go up and down and back, or if we just went down and back, we'd still have the same energy as long as we're at the floor. And so this is what we have here. We have the plus 28 for leg one, minus 28 for leg two, and 0 for leg three. And so those cancel out and you end up with 0. Same thing with the heat of reaction, the delta H, that is 48, minus 48, and 0. But look at the work and the heat. Those are not canceling out right here, these guys. Now, what's interesting is if you're not paying attention, or if you're if you just look at the net values, it looks like we've taken 16 kilojoules in and produced 16 kilojoules of work. So it looks like it violates the second law of thermodynamics, right? This is a cycle, and it looks like it took in 16 kilojoules and turned those into work, but it didn't. It took in 48. So in calculating, whoa, why did it do that? I told it to ignore my hand gestures on this thing, but it didn't. Okay, so here it took in, this is the N, Q, N. We have a very difficult time capturing the 28 and the 3, okay? So this net value is kind of misleading. We paid for this. We put this much heat into the system. How do I know? Well, we had to heat the system. And how do you heat things? You gotta burn something. You gotta generate electrical resistance or whatever. The heat in is what we paid for. That's my most basic way of saying that how these things work is you gotta pay to put the heat in. So we put in 48 kilojoules and we only got out 16 kilojoules of work. This is real. We can measure that. We can measure how much work we got out of it. This is lost to the surroundings, and it's very hard to capture that waste heat. Now maybe we can like put a side process on there to capture the waste heat, and that's great. We can use it for some other kind of engine, but we're kind of using what we've already paid for. But this might be the heat in for some other process, and it didn't come for free, but we're sort of recovering it some way. But this is where the cost is, the amount of heat, and it's the only one with the positive sign. So any kind of heat that has a positive sign is what we paid for. That's what we put into the system. And then the work we were able to get out is the net. When we get the net work out, we had to pay for the heat that goes in. So this is the net work for the cycle, absolute value. So we have negative work, which means the cycle did work on the surroundings. That's good. But to calculate the efficiency, we just take the magnitude of it. We don't take the sign. Divided by the heat in, because that's what we had to pay for. So this is where. We provided that. And so this is going to be the 16.3 kilojoules over 48.2 kilojoules. Your efficiencies are unitless. It's joules over joules. And so it's 0.34 efficient, or 34% efficient, which is really, really good. That sounds bad, but heat engines are just not that efficient. So there's always room for improvement. But this is pretty good. And the reason, what makes this good is because our temperature range is so big. We have 240 degrees versus 12 degrees. Okay, so that's our cycle problem. If this were a Carnot cycle, like which we'll talk about in another couple of lectures, there's a real simple calculation for the efficiency. The T cold over the T hot, 1 minus that. And so we could calculate that. It should be, if this were the most efficient cycle that we could make with adiabats and isotherms, no abrupt changes like these isobars and isocores, it could be 95% efficient with these temperatures, but our cycle is not a very efficient cycle. And so the work that comes out of that cycle is the efficiency times the heat in. So if we put in 48 kilojoules, we should have been able to get 45 kilojoules out of this. So how much improvement would there be in our cycle with our temperatures, which we're already capable of achieving in our cycle? We have 12 Kelvin and 243 Kelvin. We should be able to get 2.8 or 280% improvement if we were able to make this a Carnot cycle. So we'll look at that in the future. What is a Carnot cycle? The rest of the notes in your handout and so on are related to the Stirling engine, and I'll bring that on Wednesday. So we'll get to look at that, and that's what this is. So we'll go through the Stirling engine specifications on Wednesday, and I'll bring that little demo, and we can see it work. So it's really fun. Let's see you then.